Hello and welcome to this video. We will learn here the relation between shear stress, which we learned about before, and shear strain. So we'll first learn about what is really shear strain and its relation to shear stress. So it's a good question. What is really shear strain? In normal stress and strain, it's very straightforward. If I have a tension, then the strain will represent the elongation. If I have compression, it's the contraction. Now, what about this action here? How I can represent a deformation for such an action? So shear, we're looking here at that representation for it and on a 2D stress block. So go back to the video on stress blocks in 3D and 2D. I'm only showing here shear stresses. I'm not showing normal stresses. If this is a 2D stress block in the XY plane. So I only show tau XY, tau YX, and we learned also before that they are equal. So now if you look at tau YX and tau XY and on this, 1 minute, on this face here and this face here, they are equal, and these two also are equal. We can actually do statics and figure out that these two will join forces and create a resultant exactly in the midline between them because they are equal. And these two will also create a resultant in the middle line, which is kind of the diagonal line of this block. So now I have resultant of two equal forces and a resultant of the same values but now opposite. So that will create kind of a tension of this block, diagonal tension. And that diagonal tension will change the shape of the block from a square to a rhomboid. And it's still equal sides, so we're not causing any elongation of any side, but just the angles are kind of squeezed on one side or opposite corners and expanded or increased on the other two corners. And this is what we are looking for to quantify a shear strain. It is the change in the angle, and that change in the angle here we call it gamma. So gamma xy is the change in the direction of the cube lines. So we can see here that this side here kind of lifted up, this side here kind of tilted to the right, and because of that, these kind of combined tension, kind of, which is interesting. You're creating elongation of the diagonal elongation of the cube here, or the square. So what we're looking at here, gamma x split half here and here, but gamma xy is really here the shear strain. Remember, axial or normal strain was unitless. Angles are also kind of unitless, so we're still in the same lines here. Same understanding. This is another representation of the shear strain. You just put this rhomboid on flat on its side, and it will be the same kind of thing, but different representation. So different textbooks represent the shear strain in a different way. Now, shear stress and strain relation. We've seen similar curve when we discuss the normal stress and strain relation. So exhibits the same behavior. So we have here a linear relation up to a tau proportional limit, which is kind of the borderline between the elastic and plastic. We have here gamma proportional limit. So this is a linear relationship, and then you have a plastic nonlinear relationship up to tau ultimate, gamma ultimate, and then you start having here the failure at tau fracture or failure and gamma fracture. So this linear relationship also is kind of following the Hooke's law. But now instead of E, Young's modulus for the normal stress, I have G. which is the modulus of rigidity or shear modulus. So which is the ratio between tau and gamma, that linear relationship. So tau is equal to G times gamma. Now tau can be tau xy, or can be tau zx, or can be tau yz. G is relating between the shear stress and strain in all planes or all faces of the 3D general state block. One thing to note here that there is no impact of Poisson's ratio here. So the Hooke's law stays linear or simple in its form. So where there is no impact of gamma xz on gamma xy, because when this rhomboid, if we go back, this side here, if you look at it 3D, it stays square in the 3D, kind of in depth. So there's no change in the angle of that square. The only change in the angle happens in this plane xy. So this means that these Hooke's law formulas in the 3 dimensions will stay unrelated. There's no Poisson's relation or impact here. Now the question is G, how to calculate G? Similar to E, we calculate it from lab experiments. So we do a test, and I will leave this for you to see in the lab session, but there's no direct way to calculate gamma, because gamma is hard to measure. But we actually calculate torsional angle or twist angle, and you use the twist angle to calculate gamma. So, but I will leave this for the lab instructor to cover that. But we have the lab experimental way to figure out G, or actually there is the relationship that relates 3 values here. So G, E, and Poisson. It's kind of relating the 3 major material properties that we covered so far. So E, Young's modulus for normal axial stress, G, the shear modulus, and Poisson's ratio, nu. So I will leave for you to check in the textbook the derivation of that formula, but it's actually a very handy formula, because if you know 2 of the material properties, you can get the 3rd one. So that was a short video here. We just covered the we covered shear stress before, but we didn't cover shear strain. So we covered here shear strain. It's the change in the angles of that stress square, and relating it to shear stress through shear modulus, and we'll also learn about the relation between shear modulus, Poisson's ratio, and Young's modulus. Thanks for watching, and see you in the next video.